Hello, guys. Good morning to all of you. Am I audible? Am I visible? I hope everything is clear and we can start our class. Okay, so today is 23rd of February, Tuesday, and we are going to discuss basic of quantum mechanics. And we know a lot of things are there which you should know before you starting quantum mechanics. I hope the audio and video is clear. Yes, the audio and video is clear, I hope. So guys, before we start, let me just tell you this is our class schedule on Unacademy. Every we take special free classes. These are free classes on every Thursday, Friday and Saturday, 6:30 p.m. to 7:30 p.m. And one Friday we are taking it at 9 to 10 a.m. on Unacademy's YouTube channel. And every from Monday to Saturday, 9 to 10:30, we are taking plus classes on Unacademy Plus. And these are some plus classes which are already going on Unacademy. So this is batch course taken by me, Anjali ma'am, and Om sir. And this one course is going complete course on thermal and statistical physics. Here we are covering the whole syllabus in detail. And this detailed course on electromagnetic theory, this has already started, and we are going to take the second class of this course today at 9 p.m. So just enroll for this course, and if you have not taken Unacademy Plus subscription, you can take it using our referral code PHYSICSHUB. And this new batch course is going to start from February 2020 to February 22, 2021, and these 5 educators will be taking this course, and the whole syllabus of CSI and physical science will be covered by May end. Okay. Now before going to start quantum mechanics portion, let me just tell you what is the mass distribution in case of quantum mechanics from the previous few years. So you can see from December 2017 to June 2018, June 2019, December 2019, on average around 30 to 35 marks you can expect from quantum mechanics. So this is carrying a heavy weightage. So you must prepare for this particular subject. And if you look at the syllabus, you'll see what is there in the syllabus. It has core part as well as advanced part. So in the core part, you see wave particle duality, Schrödinger equation, time independent, time dependent, eigenvalue problems, particle in a box, then harmonic oscillators, tunneling through a barrier, wave function in coordinate presentation, momentum representation. Then we have commutators, Heisenberg uncertainty principle. So these many things are quite easy. And you see a few topics are there like particle in a box, harmonic oscillator. From this topic, questions are very frequent and they are very easy to answerable. Questions come from these particular topics. Dirac notation for state vectors, motion in a central potential, orbital angular momentum, then hydrogen atom, Stern-Gerlach experiment, then perturbation, identical particle, variational method, and time dependent perturbation portion is very important, and you get 5 marks question from time dependent perturbation theory. And in the advanced part, you see what is there: spin orbit coupling, LS coupling, fine structure, WQ approximation, then scattering and KGF equation and Dirac equation, relativistic quantum mechanics, Born approximation, these many things. So if you look at the syllabus is not so small. It's a huge syllabus, like next to EMT. I think EMT is having the largest syllabus, and after that it comes quantum. Okay, so you should know about these things very well. Okay, so without any further delay, let me just tell you where this classical physics failed. So classical physics basically failed in 2 domains. In relativistic domain, it failed, and in microscopic domain. Microscopic domain means where you go to very fine thing, like on atomic level. So on atomic level, this classical physics failed. in Einstein's 1905 theory of relativity showed that the validity of Newtonian mechanics ceases at very high speed. So at very high speed, if is v is approximately c of the order of velocity of light, then Newtonian mechanics cannot explain things, because Newtonian, the basic mathematical thing of Newtonian mechanics is F equals to mass time acceleration. Now what happens? This mass was taken constant in Newtonian mechanics. But as you know, when you are moving relativistically, a particle is moving in a relativistic speed, this m is no longer a constant, but it varies like m naught into gamma. Okay, m naught is the rest mass, and this gamma will decide how much change will be there in the mass. So it will depend upon the velocity with which the particle is moving. In non-relativistic velocities, very small amount of velocities, this change is not appreciable. But when you are going into relativistic domain, this change is quite appreciable. So on those domain, this relativistic domain, the classical physics failed. Now in case of microscopic domain, as soon as new experimental techniques were developed to the point of proving atomic and subatomic structure, it turned out that classical physics fails miserably in providing the proper explanation of several newly discovered phenomena. What are those? So it became evident that the validity of classical physics ceased at the microscopic level, and the new concept had to be invoked to describe these new concepts. Okay, and one of the concepts among these is black body radiation. Black body radiation could not be explained using the conventional classical physics. There we have to take up some approach of quantum physics. Okay, now let me just tell you particle aspect of radiation. Particle aspects of radiation. Now you know that in classical physics, if we have a particle, let's say particle of mass L, what do you know? What do we require to describe the motion of the particle? We require to specify the energy E, the momentum P of this particle in classical physics. Okay, in classical physics, if you want to describe a particle, you need the mass, energy and momentum of that particle. Okay, momentum P, energy E. Now if you want to express a wave, then what do you require? If you want to describe or characterize a wave, we need to know about its wave vector given by k, and the magnitude of this wave vector is k equals to 2 pi by lambda. KGF Prince, hello. So at any point of time, if you think you have a question, you can just ask me. This is a live class. That is the point of taking live class. Otherwise I could have uploaded recorded video, but here you get an opportunity to ask me any question. Okay, now according to classical physics, this wave and particle, this particle and wave, they were considered to be exclusively mutual. Okay, exclusively mutual. So according to classical physics, there is no relation between particle and wave. Now by taking this rigid concept, certain phenomena like black body radiation, then Compton effect, photoelectric effect, these many phenomena were not being explained or could not be explained using the rigid concept that radiation is only having wave-like nature. These phenomena like black body radiation, Compton effect, photoelectric effect, these phenomena can only be explained if you consider that radiation is also having some particle aspect. In addition to wave aspect, it is also having particle aspect. If you consider that, then only you can explain these phenomena like black body radiation, Compton effect, photoelectric effect. But in classical physics, this concept was not there. So we need to do some modification in the classical physics to explain these phenomena. And in today's class, we are going to discuss about this black body radiation in a little detail. Okay. Now let's start with black body radiation. Yes, Einstein got Nobel Prize for photoelectric effect. Black body will which absorbs all the wavelengths instead on it, and in case of emission is possible. Yes. Okay. So yes, KGF. Let's look at the definition of black body. Black body radiation. So what is a black body? Just look at the definition. मैं वीडियो थोड़ा सा ज़्यादा ही बड़ा हो गया. A black body is an idealized physical body that absorbs all incident electromagnetic radiation. Electromagnetic radiation, one of the example is light. Okay, electromagnetic radiation regardless of frequency or angle of incidence. Okay, so if you have a black body like this, it will absorb all type of electromagnetic radiation, whether it is falling normally or by making some angle. It will absorb everything. This is let's say black body. Now, when it is absorbing all the types of radiation, it will also emit all the types of emission perfectly. So ideally, if it is absorbing all types of radiation, it will also emit all types of all types of radiation in the form of electromagnetic wave. Okay. Now, why does some object, when it is heated, emit some radiation? Now, let's say we have some object. Now, if you heat it, then it will emit electromagnetic radiation. Why it is so? When an object is heated, it emits electromagnetic radiation because this is the result coming from the thermal agitation. Because of thermal agitation of electrons on its surface. Okay, so if you consider some spherical object like this, you are providing heat into it, then the thermal agitation will be having between different electrons, and as a result of that, the energy will be coming out in the form of electromagnetic radiation. Okay, now it will depend upon the temperature. The nature of this electromagnetic radiation will be depend upon how much heat you are providing, means what is the temperature you are creating. Okay, now let me just tell you one thing, that a black body is a perfect absorber as well as a perfect emitter. Okay, so a black body, so we can write it as a note, a black body is a perfect absorber as well as a perfect emitter of radiation. Now you see, the emitted radiation will cover the whole range of spectrum. So here I have attached a photo. You can see in this photo that here spectral irradiance, some intensity, you can basically say intensity, is plotted against wavelength, and you can see it is covering the whole visible wavelength around from 400 to 700. So it is covering the visible wavelength as well as UV and infrared as well. So it is covering basically the whole range of wavelength. मेरा picture थोड़ा ज़्यादा ही बड़ा हो गया ना, covering the whole thing. So this is the conventional black body radiation curve, and you see all of it is having a peak. So this curve is having a peak at this point, this curve is having a peak at this point, this curve is having a peak at this point, this curve is having a peak at this point. So you see, as you are decreasing the temperature, the peak, let's say we are calling it lambda m, this peak is shifting towards right, isn't it? So as you increasing the temperature, the peak is shifting, lambda p is shifting towards right. So as we decrease or decrease the temperature, the lambda m peak is shifting towards right. Shifting towards right means lambda is increasing, or in opposite sense you can say, if you are increasing the temperature, lambda m is decreasing. Okay, because lambda m into T, this is equals to constant. So this is being governed according to this relation. Now lambda m into T equals to constant. So I hope this is understood. Next, we will be talking about Wien's distribution law. Wien's distribution law. So as you can see, this is the experimental black body radiation curve. Now, how to explain this Wien's black body radiation? Sorry, how to explain this black body radiation curve? Now, different scientists gave different models to explain this black body radiation curve. Now, this is the actual distribution of black body radiation curve. But initially, this black body radiation curve could not be explained. So some scientists gave their opinion about this black body radiation curve. Few could explain only the lower wavelength portion. Few could explain only the higher wavelength portion. Okay, like Wien's discussed this lower wavelength portion. Then Rayleigh would discuss some other portion. Ultimately, Planck's gives his theory, and according to Planck's quantum theory, this whole black body radiation curve was properly explained. Now, what is Wien's distribution law or Wien's approximation? This is also known as Wien's approximation. Wien's approximation, or it is also known as Wien's distribution law or Wien's law. Okay, so it basically describes the short wavelength regime. It describes the short wavelength regime, means the high frequency portion. Short wavelength regime. Short wavelength means high frequency. Means it explained this portion. Let's say if you consider this portion, this is the short wavelength regime. Short wavelength regime. So this was explained by Wien's, and Wien gave this formula: I, intensity of, this is a function of nu and T. This is equals to 2h nu cube divided by c square e to the power minus h nu by kBt. Okay, this is and what is I of nu T? What is I of nu T? This is the amount of energy per unit surface area per unit time per unit solid angle, okay, per unit frequency. कितना पार हुआ है? Per unit frequency. Okay, so this is the formula, and this this Wien's distribution law could explain only this lower wavelength side or high frequency side. And if you express this I in terms of lambda, this will become I of lambda T. So this is will be 2hc square divided by lambda to the power 5 e to the power minus hc by lambda kt. Okay, nu equals to c by lambda. If you put nu equals to c by lambda, then you get this relation from this. So as Wien's distribution law failed in explaining the higher wavelength side, this higher wavelength side was described by Rayleigh distribution formula. Okay, so next thing we are going to discuss is Rayleigh's energy distribution. Rayleigh's energy distribution, which could explain the higher wavelength portion. Okay, now according to this Rayleigh's wavelength distribution, the total energy per unit volume, total energy per unit volume in the cavity, let's say the cavity which is emitting the black body radiation. Okay, so total energy per unit volume in the cavity in the frequency interval, nu to nu plus d nu in this infinitesimal range is given by, okay, u nu d nu 8 pi kbt divided by c cube into nu square d nu. And this Rayleigh's wavelength, Rayleigh's energy distribution, it could explain the higher frequency side. Means the lower frequency side was described by Wien's law, and the higher frequency side was described by Rayleigh's law. Okay, so it accurately describes the higher wavelength portion. Okay, so this is in terms of frequency. You can also express it in terms of energy, lambda, u lambda, d lambda. This is equals to 8 pi kt by lambda to the power 4 d lambda. Okay, so in this way Rayleigh tried to describe the black body radiation curve. So here in this figure you can see, where is the figure? Yes, here in this Rayleigh energy distribution figure you see Rayleigh, okay, this has been plotted intensity versus frequency. Okay, so long wavelength, it could explain the long wavelength portion. Long wavelength means short frequency, and this curve is plotted with respect to frequency. That is why the Rayleigh is describing the low frequency side, or means higher wavelength, and this is the observed. So you can see after a certain regime it is not explaining the observed black body radiation curve. So comparison of Rayleigh's formula for the spectrum of the radiation from a black body at 1500 K, means a black body we have which is kept at a temperature of 1500 K, then it will emit some electromagnetic radiation or black body radiation. That black body radiation is plotted here. Okay, and it is being explained using Rayleigh's law. And as per the curve, it is seen that there is a discrepancy. Here you see the discrepancy that the Rayleigh's cannot explain. This discrepancy is known as the ultraviolet catastrophe because it increases with increasing frequency. The failure of classical physics led to Planck to discover the radiation is emitted in a quantity whose energy is H. Okay, so when this energy is emitted, this is not emitted continuously, but it is emitted in the form of energy quanta having energy h nu. Energy quanta having energy h nu, like this, h nu. So from this we will start Planck's radiation formula. Planck's radiation formula. So you see how we are being directed to use quantum mechanical formula. So according to this Planck's radiation formula, energy is basically discrete. Now we are completely discrediting the continuous nature of energy which we took in classical mechanics. Now we have come to a situation that we will consider energy to be discrete or quantized. Okay, so according to Planck's radiation formula, we have radiation. The radiation has discrete energy analogous to oscillator. analogous to oscillator and is given by En equals to, in units of h nu, so n h nu, n can be 0, 1, 2, dot dot dot. Now according to this Planck's radiation formula, black body radiation, total energy per unit volume, total energy per unit volume. So we have considered some cavity, and this cavity is maintained at some temperature T. Let's say it has been heated, so it will emit electromagnetic radiation. So we are talking about this energy. Okay, the total energy per unit volume in the cavity in the frequency interval, from nu to nu plus d nu is given by u nu d nu. This is equals to 8 pi h by c cube into nu cube e to the power h nu by kt minus 1. So you know these photons. So here electromagnetic cavity radiation is basically photons, and photon, you know, the spin of photon is 1h cut. So these are boson. So this is basically followed from Bose-Einstein distribution law. Okay. So you see, this is the black body radiation curve. U nu d nu equals to 8 pi h nu cube by c cube e to the power h nu by kt minus 1. Now what is the speciality of this law? What is the speciality of this law? So if you apply high frequency approximation or low wavelength regime, it will give you Wien's distribution law. If you apply this law in low frequency domain, low frequency means high wavelength. So if you approximate by taking high wavelength, this will give you Rayleigh-Jeans law. Okay, so let me just tell you how it is given. So Planck's radiation formula is given by u nu d nu. This is equals to 8 pi h by c cube nu cube e to the power h nu by kt kBt minus 1. This is a black body radiation. Now if you write it in terms of lambda, what you can write? You can write it u lambda d lambda. Okay, so this will become 8 pi h and c into lambda to the power 5 d lambda divided by e to the power h c by lambda kt minus 1. So this is in terms of frequency, this is in terms of wavelength. This is a Planck's black body radiation. You have got it from this relation, c equals to nu lambda, means nu equals to c by lambda, or d nu equals to minus c by lambda square d lambda. Okay, now we are going to consider two cases. First case we will consider on long wavelength, on longer wavelength side. So this should give you back the Rayleigh-Jeans formula. Okay, long wavelength means a small frequency. If you do this approximation on longer wavelength or small frequency, it should give you the Rayleigh-Jeans theorem back. So if longer wavelength means hc by lambda, lambda is much greater, so long wavelength, so it will be much less than kBt. Okay, so hc by lambda means h nu is much less than kBt, or you can write h nu by kBt is much less than 1. Okay, then, or you can also write here hc by lambda kBt is much less than 1. So if let's say we have e to the power x, if x is much less than 1, we can write it 1 plus x. Can't we write it 1 plus x? So here x equals to hc by lambda kt. So if you write e to the power hc by lambda kt as 1 plus hc by lambda kt, then this 1 will get cut down. Okay, so you just write it in that way. So u lambda d lambda equals to 8 pi kt. What was the formula? 8 pi hc by lambda to the power 5 d lambda divided by e to the power hc by lambda kt. We are writing at 1 plus hc by lambda kt minus 1. Okay, so you have written the exponential in this way, and what it will produce? This will produce approximately, this is basically approximate value, u lambda d lambda. Okay, so this one and this one get cancelled, and you are left with 8 pi kbt by lambda to the power 4. 1 lambda is getting cancelled. Okay, hc is hc getting cancelled into d lambda. 8 pi kbt by lambda to the 4 d lambda, and this is the Rayleigh's formula. So at long wavelength regime, we are getting back the Rayleigh's formula. Next, we are considering case 2. Case 2 on shorter wavelength regime. Short wavelength. Short wavelength means high frequency. Short wavelength means high frequency side. What do you get in high frequency side? So if it is high frequency, hc by lambda, lambda is very small, so it will be much greater than kbt. It means hc by lambda kbt, this would be much greater than 1. Okay, then what will be the form of this u lambda d lambda? So e to the power x, if we have x, and if x is very large, e to the power x will be much greater than 1. Okay, so in this formula we can just ignore this one, because this term is very much high term. hc by lambda kt is much greater than 1, so e to the power that is even much greater than 1. So with respect to that, we can just ignore this one. Then we can write it in this way: u lambda d lambda, this is equals to 8 pi hc by lambda to the power 5 d lambda. Okay, and e to the power minus hc by lambda kt is only there, and this one is just ignored, because this e to the power hc by lambda kbt is much greater than 1. This plus na, e to the power hc by lambda kbt is much greater than 1. Okay, so this is approximately give you 8 pi hc by lambda to the power 5 e to the power minus hc by lambda kbt d lambda, and this is your famous Wien's law. Okay, so you see how compact this Planck's radiation formula is. Okay, so I'm again explaining the whole thing. Let's say we are considering intensity versus wavelength. So this is the actual curve, and this actual curve was explained by Planck's radiation. Okay, and the low wavelength portion, this portion is described by this Wien's law, and this high frequency domain is being explained by Rayleigh's. Okay, and these two people utilize classical assumption, classical physics, and that is why they could not explain the total spectrum. But in case of Planck, the smart Planck, what he did, he just gave up this classical physics assumption. He utilized the idea of quantum mechanics, quantum physics, and he got the observed curve. So this is actual curve, and this curve is well fitted by Planck's distribution. This is basically observed, or this curve is also Planck's curve. So you see how Planck's radiation formula is so important. I hope all of the things are clear. Any question? We are almost at the end of the class. If you have any question, you can just ask me. regarding this or anything else? Do you have any question? Okay guys, so you see, you can take Unacademy Plus subscription. There's a lot of benefits of there. You get daily live class, part length, full length test, assignment, the detailed solution, dedicated doubt clearing session. The whole syllabus is covered. You get a proper structured course. And if you have not joined our Telegram group, you can join using the link given in the description. And these are the courses which are currently ongoing every day at 9 p.m. And this course is starting. That's one class has been done, and today we are going to take it another class from 9 p.m. So enroll for this class. You will get the link in the description. And this batch course is going to start from 22 February. So you can also join that. And our approach is I precisely give you the concept of the concerned topic. We discuss relevant mathematical formula, do the analysis, relevant problems based on the topic, including previous year questions. Homework and assignments are also given to the students. And you see, this is a kind of fee structure for Unacademy. You can just take it if you utilize our referral code PHYSICSHUB. Okay, PHYSICSHUB. Then Unacademy will give you 10% off. Okay, so we'll keep on discussing these things later on. And today we have to say goodbye to you. Okay, what is the question? Was Planck's idea put forward after Einstein quantum theory of light, which he used to explain photoelectric effect, made part of the frequency? Okay, so you can see was Planck's idea put forward after Einstein's quantum theory of light, which he used to explain photoelectric effect. Yeah, this kind of at the same time domain, Einstein was discovering this photoelectric effect, and Planck was doing separately. Planck also got the same vibe. Like Einstein also considered that the wave or radiation which is incident on some metallic surface, this nature of this is quantized. In the same time, Planck also were investigating the same thing about the black body radiation. So it was just a coincidence that Planck also considered that the nature of the energy carried by some radiation is discrete in nature. Okay, so this is around 1900 to 1905. In this time, people starts thinking about the discrete nature of radiation. And you know, in specific heat also Einstein considered the discrete energy nature. Basically, Einstein used the result of Planck. Planck was the first to consider this. Einstein basically utilized Planck's this result to explain specific heat. Okay. Avinash explaining it mid part. Mid part actually the what I can say. Yes, this region, the mid part is like it is getting flat. This portion was being described by Wien's law, and this portion by Rayleigh's law. Okay, Rayleigh's. The exact relation is lambda m into t. Okay, lambda m into t equals to constant. Now, as the temperature is decreased, the curve is getting flat. Okay, so if you are considering, so this is basically Wien's law, and the remaining portion is described by Rayleigh's law. That is the thing. I hope all the question is clear now. So I am ending the session. If you have any other question, you can just ask me now, or we'll just finish the live. Okay. So thank you very much guys for joining the session, and see you in the next live session. I will let you know in the group. So join the group. The link is given in the description, and have a great day. Bye bye.